Our speaker tonight is Palash Banerjee, and he's currently assistant professor in the Department of Physics and Astronomy at UWSP. He joined our faculty, and I'll never forget talking to you in my office. It was a wonderful time. He joined us in the fall 2011. He's been here 2 years, and he's in his third year here, and we've gotten to know each other pretty well. Probably much of it through my reading of the grant applications that he consistently sent to us. And I encourage you to do that as well. He received his undergraduate and master's degrees of physics from the Indian Institute of Technology at Kharagpur, that's right, in India, and his PhD in physics from Boston University. His PhD thesis involved studying how supersonic helium atoms bounce off a rough surface. I just think that's a great description. It just brings visions to mind here. He then joined the Ohio State University, of which we will not hold him accountable because I'm an Indiana University guy, for his postdoctoral studies, and he changed his research topic and began work there in the field of magnetics, which is what you're going to talk about tonight. While he was in Ohio, he was lucky enough to acquire varied experience involving a trip to Dresden, I believe it was, Dresden in Germany, as a visiting scientist, and he also taught at a private liberal arts college in Ohio, Denison University, as a visiting assistant professor there. So he's had quite a bit of teaching experience and a lot of research experience. His current research interests include studying the magnetic properties of materials in building instruments to measure extremely weak forces. And his other interests are travel and long-distance bicycling. And I want to welcome you to this community lecture series tonight.
Thank you.
Thank you, everyone. Thanks for coming. Let me start by just explaining what this title means. I'm interested in looking at small magnets, and I'm interested in finding out how they behave, and I'm also interested in sort of tickling them and seeing how they respond. And so when we look at small magnets, we have to build instruments that have the capability to look at objects that are that tiny. And so that's where the ultra-sensitive part comes in. And so I'll be describing to you the instrument that me and my students are building to do some of the experiments that we have in mind. And I'd also like to first tell you why you should care about small magnets. And so there's a good reason, and I hope to convince you that it's worthwhile looking at how small magnets behave. Well, let me start off by, maybe I should acknowledge who's been paying for all of this. Thanks to the university, the College of Letters and Science, the physics department, and also an applied research grant from the UW system. And so they've been paying for all of my laboratory experiments. And I also want to acknowledge some of my students, both former students and current students. Most of the work that I'll talk about is due to the fact that these students were part of my lab. Ed Lynch, Alex, and right now I have Sean, Erin, and Kyle working with me in the lab. So let's talk about magnets first, before we even get to small magnets. People say magnets are useful, and do we agree with that? Well, yeah, could be they have uses. Refrigerator magnets. And so everybody says, oh, you hear the word magnets, and the first thing that comes to mind is refrigerator magnets. Useful. Could we live without them? Yeah, we could. Yeah, so they're not that useful. Good to have them. Let's move on to the third point. What if I told you that magnets can be used to produce electricity? Would that be true or false? True. Not really. I mean, when you enter the room, you throw a switch, really. Where is the magnet involved? I would say switches can be used to produce electricity. But that's not really true. And so let's see how you can use a magnet to produce electricity. And so here is an example of a large magnet. There's nothing nano about this. This is a big hunking piece of magnet. And if you try to lift it up, you will realize that it's big and heavy. What I'm going to do is I'm going to show you the principle or the basis for all of the technology, which is electricity after all. And electricity is something that we cannot live without. And so here is a loop of wire, and at the end of the wire is a little light bulb. There is no switch here. There is no power supply here. There is no battery involved. But I claim that I can get this light bulb to glow just by waving it near a magnet. And so I hold the magnet, I hold the bulb, and then I start wiggling it back and forth. And the longer I wiggle, the brighter. If I stop wiggling, no electricity. It's only the motion that produces electricity. And so magnets play actually a very important role in our lives. This is the basis for all the electricity that powers our homes and our cities. Somewhere, someplace, a coil is moving near a magnet. And so that's sort of the motivation for why magnets are interesting and magnets are relevant. There is another place where magnets play perhaps a very important role. So I'm going to show you this picture and ask you to guess what this might be. Well, this is certainly an airplane. But what about this other large object? Computer, okay. Anybody else? A generator, okay. Magnet, okay. Anybody else? Well, it's related to a computer. This is the first hard drive produced by IBM, all the way back to 1956, so almost 60, 70 years ago. And look at the size. This was almost 1 ton. And this is not the computer, this is just the hard drive. And so this weighed a ton, and at that time it could store 5 megabytes. And so I did some conversion, and I came up with this idea. So you needed half an SUV to store 2 songs. So that's how I like to think of this. And look how far we've come in these 60 years. Now hard drives are, you can carry one in your pocket. And I'm going to pass one around so you can take a look at the inside of a hard drive. This is not state of the art. This is about 10 years old. But it gives you a sense. This does not weigh a ton. And so where are the magnets here? And so let's talk a little bit about how information is stored in your hard drive. And the hard drive does depend on a collection of very tiny magnets. And that's how all your data is getting stored in the hard drive. Your files, your music, your other things, they are all stored on your hard drive, and your hard drive consists of a large number of very small grains. And so let's talk a little bit about what we need to know to understand how data is stored. Here is a magnet, and so this is hanging in the form of a pendulum. And what you really need to know is how this magnet responds to another magnet, which is in my hand. And you will see that it can behave in 2 different ways. It will either move away, or it will want to come close. And so this behavior, I can just classify it in 2 ways. Either it wants to come close, or either it wants to move away. And I can call these 2 distinct kinds of behavior to be 1 or 0, just representing these 2 different ways that this magnet behaves as 1 and 0. And so any information that I want to encode, I claim can be encoded using magnets. In one case, the magnet can be pointing up, and in the other case, the magnet can be pointing down. And if I arrange a whole array of these magnets, up, down, up, down, down, up, down, up, I'll be able to store any information that I want. And so a very language independent way of storing information. A method that is independent of what is it that you actually store. All you care about that these magnets can be lined up such that either they're pointing up or they're pointing down. And these are familiar to you. These are what we call as the bits of information storage. And so the reason you don't see this on the hard drive that I passed out is these bits or these grains are very tiny. So for example, this blue region can represent what we call 1, and this gray region represents what we call 0. And the size of these regions is very, very small, a few hundreds, maybe 1,000 nanometers. But there are a whole bunch of these things on your hard drive. And the goal really is, if you want to pack in a lot more information into your hard drive, let's try and make these regions smaller and smaller. And so your hard drive stays as is. You're able to pack in more and more information into your hard drive, provided you make these grains smaller. And that is what has been going on for the past 60 years. People have been figuring out that, yes, we can still continue to shrink the size of these magnets that hold all of our information. And so the hard drive industry has a goal, a very clear goal in mind. And the hard drive industry says that we want to produce a hard drive which we can sell. And the goal is that this hard drive should store 1 terabit of information in 1 square inch of real estate. It's a very clear goal, and all the major players in the hard drive industry are furiously trying to reach this goal. Right now, state of the art is half a terabit per square inch. And so you might say, what's the trouble in going from half to 1? And that's where the big trouble is. And so I'll explain why this last step is taking so long. Just to keep things in perspective, 1 terabit is roughly 250 movies, full-length movies. And this is half a square inch, a nickel. So the game is on. Toshiba, Samsung, Hitachi, and Seagate. And each of these companies are furiously trying to reach this goal. Take this disk, make it twice as large, you have 1 square inch. Into this disk, cram in 250 movies. Do it in a way that people can buy it. And so make sure that you understand the science, and make sure that your engineering is such that you can produce this device at a reasonable cost. And whoever is the first to the market, I think they will take over the market. So what's the problem? Just make it smaller. And the problem is, when you make magnets a little bit smaller, they don't behave the way they should, or they don't behave the way large magnets behave. And that is currently the problem people are facing. People don't quite understand, even at the basic scientific level, what really happens when you make magnets really, really small. At some point, the magnets don't behave as magnets.
May I ask a quick
Yes, please.
question on the previous slide?
Uh-huh.
What exactly is meant by plus magnetization and minus or negative magnetization?
Plus magnetization just means that the magnet, one end of the magnet is facing up, the north end, and the minus means the south end is facing up. Yeah. So each magnet, and no matter what the shape, has 2 ends. And so one we call plus or minus, or 1 or 0. Yep. Yes, please.
How does a DVD storage compare to this, where light is somehow?
So DVD,
The DVD disc?
right. So the DVD storage does not depend on magnets at all. So the way DVD storage works is you have a very soft polymer coating on a glass, and then you're able to etch little pits using blue light. As in terms of storage density, I think the DVDs don't come anywhere close. So you're able to cram in a lot more information using magnetic grains than you're able to cram in using light. Yes?
What are those grains made out of?
Some magnetic material, typically proprietary alloys, but as far as I know, it's a mixture of cobalt and platinum and iron and rhenium. So you need some magnetic material to make sure that, after all, it's a magnet, and you need some other materials to make sure that those magnets don't rust. And each company has its own proprietary version, but it's, which they never tell you, but it's an alloy of a few different metals. Yes?
One more question. Could you tell us what power 10 tera is?
Tera is 10 to the 12, so 1 followed by 12 zeros. That's a good point. Yep. And so this is one possible way to imagine what is going on. This is, I think, work done at Singapore. And so what they've been doing is creating these little magnetic dimples on a surface with the goal of having an array of these dimples placed so close to one another, and that if you look at 1 square inch, you will find that you have a terabit of data. So far, this picture, you see how close these bits are? They're just crammed in really close to one another. This is a little bit more than half a terabit per square inch. And so you see the challenge. It's not so easy to shrink things down. And it's not even clear whether they will remain magnetic, first of all. And it's not even clear that if you disturb this little magnet here, the magnets next to it will not be disturbed. And that's important for hard drives. You want to be able to make sure that you flip one magnet here, but leave its neighbors unaffected. If you make them too close to one another, that condition no longer holds, and you have to think a little bit harder to make sure that you can flip one and leave its neighbors the way they were. And so people have realized many years ago that these two rules of thumb hold. Bigger magnets are more stable, and they are well behaved. But below a certain critical size, which depends, of course, on their shape and which material you use, the smaller magnets are unpredictable, and they are unstable. And so if you leave a small magnet with the north end pointing up, and you come back after a day, you will find that maybe the south end is pointing up now. And so they don't quite stay the way they should. And so that is really the focus of research in the field of magnetics. Can we understand and overcome these limits? And so people are trying many different things. One of the things they're trying